Oh, hello, this is lecture 13 after the midterm. Welcome back. We have some exciting topics ahead of us. Chi-square tests and non-parametric two-sample t-tests and analysis of variance. Those are your traditional statistical tests. And then we're going to spend a few classes talking about regression and end the course with Bayesian statistics. But today we're going to discuss the goodness of fit test, also one of the chi-square tests, and we're going to begin with an introduction to the multinomial distribution. So the multinomial distribution is a generalization of the binomial distribution. The binomial distribution is a sum of independent trials, each trial having two outcomes. P1 and P2 are the probabilities for outcome 1 and 2, and X1 and X2 are the number of occurrences of outcome 1 and outcome 2 respectively, so that X1 plus X2 is N. And the chance that you get exactly X1 outcome 1s and X2 outcome 2s out of N draws is given by the binomial formula. And I expect this is familiar. So another way to think about this is that in N trials, we observe X1 outcome 1s and X2 outcome 2s. So the O1, O2 here is for observed 1, observed 2. What do we expect? Well, X1 and X2 are each binomial, N P1 or P2, depending on whether you're outcome 1 or outcome 2. So binomial N P1, for example, as long as P is not too small or too large, is approximately normal. And we can write the sum of the observed minus expected quantity squared over expected, the sum of that, which is called the chi-squared statistic, summing over outcome 1 and outcome 2, that can be written as a single term, namely X1 minus NP1, which is basically the expectation of X1, divided by, so that's squared, divided by the variance of X1, which is NP1 Q1, because the variance for binomial is NPQ. So now that, as n gets large, approaches the standard normal squared, and that is chi-squared, by definition, is chi-squared with 1 degree of freedom. So the way to think about binomial is that if we have two outcomes here, X1 and X2 are both approximately normal, although they're not independent. X1 plus X2 is N, so there's a dependency there. And writing the chi-square statistic, you're writing a sum of two terms, which sort of look like z squares, although not quite, because you're missing the Q1 and Q2 in the denominator. But with some algebra, you can see that actually this is exactly z squared. So omitting the Q1 and Q2 in the denominator allows you with some algebra to get exactly chi-squared with 1 degree of freedom. Now the multinomial random variable is a sum of n independent m outcome cells. So instead of 2, we have now m outcomes, probabilities P1 to Pm, and the probability of having exactly x1 outcome 1s, x2 outcome 2s, and so on is given by the multinomial formula, which is just a generalization of the binomial formula. And if we know P1 and Pm, the multinomial distribution is completely specified, which means that you can calculate the probability of any outcome. Now, again, we can think of this as we're observing x1 to xm. Each of these are binomial, and if p isn't too small, these are approximately normal. And as n gets large, the chi-squared statistic approaches the chi-squared distribution with n minus 1 degrees of freedom. So just note that the chi-square statistic is a discrete quantity, and the chi-square distribution is a continuous distribution. So it is it approximates asymptotically. Okay. Okay, on to section 9.5, the likelihood ratio test. So here we're dealing with a categorical variable as opposed to a continuous variable, which we saw in chapter 11. So our null box are probabilities parameterized perhaps by theta. And so here I'm just writing P1 to P3, but you could have up to m cells, and theta itself could have, let's say, k components. We draw with replacement size n, in this case 3, we get 3 observed cells here, where x1, x2, x3 are the number of outcome 1, outcome 2, outcome 3. Now, step 1 is going to be, because our null box is not fully specified, we need to find the MLE for theta. Once we do that, we can do a goodness of fit test. So we expect these xi's are binomial, so we expect NP theta, but we don't know theta, so we use the MLE. So this gives us our expected values. And our null is that the binomial distribution in our box is what's given here. We have this null box here with our thetas. And the alternative is that we have some other multinomial distribution. Flash forward, we do a GLRT, and we're going to show that minus 2 log lambda is approximately chi-squared m minus 1 minus k degrees of freedom. And minus 2 log lambda is going to be approximately the chi-squared statistic, called the Pearson chi-squared statistic. So here's a good example, the Hardy-Weinberg equilibrium model, which gives us a null box where P1, P2, and P3 are functions of theta is shown. And, well, what we observe are phenotypes here. So M, Mn, and N correspond to double capital A, small a, and small a genotypes. And so step 1, since our null box is not fully specified, we need to find the MLE. And I did check, this is the correct answer, so you can check that. And then we can compute the expected counts given here. And our null hypothesis is that the multinomial is that we have the null box essentially. And the alternative is that we have some other multinomial distribution.